Make sure you read the experiment very, very carefully. There are a lot of details in there, which we're going to go through today. But you need to read it very carefully and be ready to act on what you need to be doing in lab and kind of thinking ahead of to what the next step is, so you're ready to move through the experiment. It's going to be a lot of things to happen this week in lab. We'll have a quiz. Make sure you bring your calculator for your quiz, as well as other calculations in lab. Your experiment 6 report is due this week too, so make sure you have that ready to go. Next week we're going to be doing experiment 10 and 11. The actual doing of the experiment in lab is experiment 11, so that's what the majority of your pre-lab should encompass, and I'll talk about that more in detail next week. But if you want to get your pre-lab together before lab lecture next week, your doing part is experiment 11, and you're taking the alcohol that you make from this week and using it in next week's experiment. Okay. Your experiment 7 report is due in your notebook, so we'll be taking your notebooks from you next week. The standard IR for polystyrene is posted on Moodle. I'm going to show you that here in a minute so that you have something to compare to. It's also posted in both labs and on the door to where the IRs are. And for your experiment 7 report, you also need to get GPC data from your instructor. So we couldn't run anyone's samples last week with the GPC because the GPC is sick. But we have GPC, we still want you to analyze GPC data. So we have data that we want you to analyze for your report. So we'll give that to you next week, or this week, sorry, in lab. And then next week is the week before registration, or week of registration, so I'll talk a little bit about registration for Chem 256 A and B next week. So the IR that's posted on Moodle is this guy, as well as what's posted in the labs. You do not need to make a copy of this because everybody would have the same copy, okay? So let's save some trees, not make a copy of it. What you do need is this peak list. In addition to what the IR spectrum looks like, you want to compare these peaks to the peaks in your own IR spectrum, okay? So look at that on Moodle. All right, so let's start talking about experiment 8. So many things to go over. We're going to be doing a Grignard reaction this week. So Grignard is capitalized because it's named after someone. Victor Grignard discovered this reaction in about 1900 or so. And in order to do this reaction, we actually need a Grignard reagent to complete this reaction. So the first thing we're going to do in lab this week is the formation of your Grignard reagent. And remember, last week in lab, you should have got a half sheet of paper that told you the reaction that you will be using and what you will be using for your Grignard reagent formation and then the Grignard reaction. So make sure you follow that. You need to follow that half sheet of paper and make sure your pre-lab follows what you got on that half sheet of paper. So your pre-lab should be specific to what you are doing in lab. So the Grignard formation of a Grignard reagent is an organometallic reaction. So we're going to involve organic chemistry with a metal. Our metal is magnesium. And our organometallic halide is our Grignard reagent. Okay? So overall, it's an organometallic reaction, but the formation of the reagent is the organometallic halide, or magnesium halide. So you will be starting with an alkyl bromide. So that's specified on your half sheet of paper, which one you're going to start with. And you'll be reacting it with magnesium. And we use ether, diethyl ether, is our solvent for this reaction. And for the Grignard reaction, there's only a few solvents that you can use to make it work well. Ether being one of them, THF is another one. What's really important about using the ether is it has a high vapor pressure, so we're going to try and keep oxygen out of our reaction because that would cause a problem with our Grignard reagent. And so what you will form is this, is the Grignard reagent, so you'd still have the same R group. So for example, if this is bromobutane that you're using, and we react it with magnesium, we will form this corresponding magnesium bromide. Okay. And so this will be formed in our reaction flask as the alkyl bromide reacts with the solid magnesium that we have in our flask. Now, this is a really important reaction as far as organic chemistry is concerned, because what we've got in this species here is something that's kind of unusual. We've actually got, so if we have different R groups on our big R group and a carbon in the center, so these could be other carbon R groups or protons off our carbon, we're forming something that gives a partial negative charge to that carbon, which doesn't happen very often in organic chemistry. Usually that carbon's going to be more a little bit towards the partial positive charge than the partial negative charge. So that's important because usually later on we're going to use this as a nucleophile. Okay? So the partial positive is on the magnesium, the partial negative is on the carbon itself. And so it can react with weak bases. And so this is also important. And so that would be things like water or alcohols, aldehydes, or even amines. And we're going to take advantage of that, but also try and prevent it from reacting with other things. Now, ether is important because of its vapor pressure. Also, the solvent is really important because you need the solvent coordinating with the magnesium. So we're talking about terms that we use with inorganic species, and the magnesium is an inorganic species. So we need that solvent to coordinate with the magnesium that helps solubilize the magnesium, bring the magnesium into solution to then react with the alkyl bromide. Okay, and so there's only a few solvents that are able to do that. Now, once we form this Grignard reagent, it's a very reactive species, so we have to be careful of potential side reactions that can occur. We talked about a little bit of that here when we were talking about our bases. So one of the things it can do is it can react with water, which we don't really want to have happen, so we're going to try and exclude water from our system. So if we react with water, what we get is the alkane, the corresponding alkane from the alkyl bromide. So like in this example, we get butane plus then we get this species here, our bromomagnesium alkoxide. To prevent this, we're going to use dry ether and we're going to use dry glassware so that we don't get any water into our system. All right? And so that's why you guys are going to be coming into lab early this week so that we can get your glassware in the oven. Okay? So remember, AM labs will come in at 7:15 to put their glassware in. PM labs about 12:45 to put your glassware in the oven. Something else that can happen is it can react with oxygen. We don't want that to happen either, because that will take away our Grignard reagent. And so what you form is this species. And this will kill our Grignard reagent in that it forms kind of the intermediate that we want to form, but then it won't go on and form the alcohol that we want it to form. And so we're going to use cotton and all the openings that we have to prevent oxygen into the reaction, okay? And then, like I said, we have a high vapor pressure on our ether to also prevent that. We can have the Grignard reagent react with the alkyl bromide, and we also don't want that to happen. And when you have that happen, basically we form the corresponding alkane where we've added two of the alkyl pieces together. So with the bromobutane, we would form octane, which isn't going to help us, and magnesium bromide. So to prevent this, we're going to slowly add the alkyl halide to the magnesium instead of adding it all at once. And what you get is then less of this formation so that the alkyl bromide is reacting with the magnesium as it's being dripped in instead of trying to react with the Grignard reagent that is already present. Now we're going to use an apparatus that we haven't used before, so it's a modification of glassware you've already used before. And so we have to take some care with that apparatus. So we talked about what glassware you needed to have clean and dry for lab this week. So it was your 3-neck round bottom flask with its stir bar. You needed 2 glass stoppers, the separatory funnel without its Teflon pieces in it, and your Liebig condenser, okay? You won't be able to clean any of your glassware this week. So whatever you've got when you come to lab is going to go in the oven unless for some reason you had like excess amount of water in it, and then we'd have to do something else. We're not going to stick it in the oven. So make sure before your lab section meets, you've got all of this glassware together and there's no evidence of water in the glassware itself, okay? So we're going to set up this apparatus, clamp our 3-neck flask. We'll have a glass stopper here, and then we'll use the other glass stopper as we're setting things up. But we'll have our separatory funnel on the other side, and you'll have to put your stopcock pieces back together again. Cotton in the top of the separatory funnel, and then in the center is the condenser, cotton in the top of the condenser. So you want to clamp your reaction flask and also have a support clamp on your condenser. You don't want to clamp your separatory funnel or anything else because we're going to need to raise and lower this apparatus quite a few times during the process of forming the Grignard reagent and doing the Grignard reaction. So you're going to have this above your stir plate, but you want to leave some space between stir plate and the bottom of the round bottom flask, okay? You want to leave space there that you could stick a pan of water underneath if you needed to, but also to start the reaction, we're actually going to warm the reaction with our hands because ether has such a low boiling point. You can get it refluxing just with the warmth of your hands on the reaction flask, okay? So you want space between stir plate and reaction flask, okay? Now for this glassware, before you stick it in the oven, make sure you label it either in pencil or Sharpie, so you hopefully get your glassware back out of the oven, but if not, everybody's putting the same thing in, so you'll get something similar to what you had back out again. And this has to heat in the oven above 110 degrees for about a half an hour, okay? So we're going to get this glassware all in the oven before we start the quiz. Then once everything's in the oven, then we'll start the quiz and do pre-lab discussion and then be able to pull things out of the oven for you to start your reaction, okay? So we want the oven shutting at 7:30 for AM labs or 1 o'clock for the PM labs. That's why we're having you come early, okay? The other thing, when this comes out of the oven, remember hot glass and cold glass, they look the same, okay? So be careful. It's coming out of a really hot oven. Don't burn yourself. Use your hot pad handling it and carefully handle the glassware as you're assembling things. When things come out of the oven, what we're going to do is we're going to stick cotton in all the openings so that it's, as it's cooling down, it's not getting oxygen and water into that glassware. And then when it's cool enough for you to handle, start assembling things. But don't try and assemble things when it's too hot to handle, because that's when dry glassware that's ready to go ends up getting broken, okay? There isn't a drying, so if you have older lab manuals that talks about using a drying tube, we don't use a drying tube on this apparatus. And what you're going to do is set up the apparatus, okay? Then you're going to get your magnesium, which you have to calculate how much magnesium to use. Weigh out your magnesium, add that to the apparatus, and be careful with the magnesium because it wants to oxidize really easily, so you want to limit how often that jar is open, as well as weigh it out in time to stick it right into your round bottom flask. Then you're going to add 10 milliliters of dry ether. So the ether that you're using for setting up the Grignard reagent formation is in the reagent hoods, okay? So dry ether, not red can ether. Dry ether. Then you have to calculate how much alkyl bromide is going to go into your separatory funnel, okay? So I would measure out your alkyl bromide, and you have to, everyone's using the same number of moles, so depending on what alkyl bromide you use, everybody's using different volumes. Calculate that number in volume. That's what you're going to measure, is a volume, not a mass. You're going to have that alkyl bromide in 40 mils of ether in your separatory funnel. Okay? So you can add the ether to your separatory funnel, add the alkyl bromide then to the separatory funnel. Alkyl bromide's more dense than the ether. As it goes through the separatory funnel, it's going to mix to make the solution that you need. Okay? So when you get to this point, you've got your magnesium and ether. You've got your alkyl bromide solution, but your stopcock is closed. You've got the rest of the setup. You've got your water in, water out. Everything's set up. Your instructor is going to come around and check your apparatus, okay? And then we'll help you with getting this. You're going to add a small portion of alkyl bromide, add some iodine to the reaction, and we're going to help you get the Grignard reagent formation started, okay? And so what you're going to look for is on the magnesium itself, it should start getting kind of bubbly and kind of grayish color. If you start seeing that, that means there's reaction happening on the surface of the magnesium, and we're going to start adding that alkyl bromide dropwise, okay, and control the addition. So we don't want it going too crazy, but we don't want it petering out on us and stopping, because it's really hard to get this reaction going again, okay? So we'll help you with this part. This is the setup that you're going to use, okay? All right. The reason that we use the iodine is we need to clean the surface of that magnesium, okay? So the magnesium plus the iodine, that's why we're going to put a crystal of iodine in your reaction, cleans or etches the surface of the magnesium so that it will be more reactive. So we talked about first your alkyl bromide is going to go into reaction dropwise. During this time, the other thing that's going to happen is you're not stirring. So the whole time that you've got your magnesium and your ether in your reaction flask and you're adding the alkyl bromide dropwise and during the entire Grignard reagent formation, you're not stirring. And the reason for that is we don't want to add oxygen or water to our apparatus. So if we stir, we're going to kick all that into the apparatus. So there is no stirring, all right? Once you've added the alkyl bromide dropwise, and we do want it refluxing when it's being added, okay? So you want to maintain reflux. So it's kind of a fine line between adding it too fast so that you get side reactions, but also it's refluxing too violently, and not adding it fast enough that it stops refluxing, okay? Then, oops, sorry, not to stir here. Then you're going to heat for about 15 minutes with a warm water bath, okay? And if you can, you want to keep that reflux going that you had with the alkyl bromide addition, okay? So once you've added all the alkyl bromide, that starts your 15 minutes. You want to keep that reflux going. If it's refluxing on its own, don't add the warm water bath because that's probably going to stop the refluxing, okay? But you want to get that warm water bath really hot with hot tap water so that when the refluxing starts slowing down, you can put that hot water in it and keep it going for that 15 minutes if possible, okay? The other thing is once your alkyl bromide is all added, close the stopcock. We're going to add more reagents through that separatory funnel, and we don't want it all dripping down in there all at once, okay? So then the next thing that you've got to do is we've got our alkyl bromide. In order to get our reaction to actually occur, we're going to add an aldehyde, and we with the Grignard reagent you're learning in lecture, you can use either aldehyde or a ketone usually to be added to that Grignard reagent to get a reaction. We're using an aldehyde. So for the Grignard synthesis, so using our Grignard reagent now to make our alcohol, you're going to have your alkyl magnesium bromide, and we're going to react that, like I said, with an aldehyde. Okay? And so remember, our carbon here with our Grignard reagent is nucleophilic. It's got nucleophilic characteristics to it, right? Because our magnesium is taking the partial positive charge, our carbon has that partial negative charge, okay? And so we can have that carbon attack our aldehyde. We have our electrons kick up to our oxygen, and again, the entire sequence is in ether as a solvent. And so we form this intermediate. And again, our magnesium does not change its partial positive charge. Our oxygen has a partial negative charge, which makes sense for oxygen to have a partial negative charge. So we get this intermediate that then we need to quench this intermediate, okay? So just reacting our Grignard reagent with our aldehyde is only going to get this far. We need to use acid to finish the workup to get our final alcohol product out, okay? And so we're using sulfuric acid. And so when we use the sulfuric acid, we get our alcohol out. which is our product that we want. Remember, our R1 came from our Grignard region, our R2 came from our aldehyde. We're forming an alcohol at the carbon that is part of the carbonyl of that aldehyde. Okay? Now this is where we want to stop, right here. We don't want any further reaction at that alcohol. But it is possible for that alcohol to go on and form an alkene, which we're going to do next week, but we don't want to do this week, okay? So you have to be careful with the quench as well to not get to the alkene. So first of all, with our aldehyde in this reaction sequence, we are going to add the aldehyde solution. So a solution is already made of the aldehyde that you're using in ether that has the proper concentration. Okay, so it is a solution. So you need to look for the aldehyde solution. Remember, refer to the half sheet of paper as to which one you use. It's really important that you use the proper one because only the amount that's going to be used by your lab section based on those half sheets of paper are put out in each lab. Okay, so you can't decide to use something else. There won't be enough reagents for everybody. You're going to add the aldehyde solution through your sub funnel dropwise. And this is a pretty exothermic reaction, okay? So before you start adding it, you're going to use a cold water bath around your round bottom flask, okay? But you don't want an ice bath. If you use an ice bath, it's too cold. You won't get the reaction to occur. So just cold water bath, and right before you are ready to add your aldehyde, you're going to start stirring. Okay? So up until this point, we haven't been stirring at all. Right before you start adding the aldehyde, we're going to start stirring the reaction. Now, this is added dropwise. We need to control its addition. We don't want things refluxing too quickly. As you're adding it dropwise, you may actually hear sounds in your round bottom flask. You may hear kind of fizzing noises of the reaction actually occurring, or you may see visually fizzing occurring as you're adding the aldehyde, which is okay, but we need to control this addition. We don't want to just add all the aldehyde all at once. To control the exotherm, but also adding the aldehyde too quickly can form the ketone, the corresponding ketone, to the alcohol product. So say you're going to make 3-octanol. What you will form if you add the aldehyde too quickly is you'll hopefully form the alcohol, but you'll also see a lot of 3-octanone in your reaction mixture. And all of this, we're going to evaluate our products with GC, so we'll see all of these impurities and have to account for all of these impurities. So be careful to add that aldehyde dropwise. Okay? When we get to adding the sulfuric acid, and once you've added the aldehyde dropwise, you're then going to stir it as well after the addition to get complete reaction for about 15 minutes at room temperature. Then, when we add the H2SO4, you're going to be making a solution from 9 molar sulfuric acid. So be careful. It's only half dilute concentrated sulfuric acid, so be careful, don't get it on you. You're going to make the solution that you're then going to put in the sub funnel. So again, we're using our sub funnel for the addition. and that is the quench of our reaction. And so if you look in your lab manual, there's a flow diagram that shows you all of the workup of the experiment. Okay, so we've got this part here is basically our big reaction mixture. What we've got to do, though, before we can continue with the reaction, is we need to make sure that we get rid of all of the magnesium solid. So a lot of this will be taken care of in this quench with this sulfuric acid, but before you go on to anything beyond adding the sulfuric acid, make sure all that magnesium is gone in your reaction mixture. Okay, so it should all react, or if it doesn't completely react, we're going to filter your reaction mixture through glass wall. But in adding the sulfuric acid, we're adding it through the step funnel again, so we're adding it dropwise. Make sure the stopcock is closed before you put it in. We want to add dropwise. This time you want to use an ice bath for around your round bottom flask, and you don't want to reflux the ether. If you're refluxing the ether, you're heating it too much. So because this so easily the alcohol so easily can form an alkane, we can get water to eliminate, we'll dehydrate it and form, alkene. We've got to control the addition of the acid. So we don't want it getting too hot. So you're going to add it dropwise, keep it in an ice bath, and make sure you don't reflux the ether. Okay? When you're done with the addition, then like I said, you'll make sure you don't have any more magnesium. And then we also need to make sure we don't have a lot of magnesium sulfate that can form from the sulfuric acid and the magnesium reacting with one another, because the next thing you're going to do is go into your separatory funnel. Okay? Now during this quench, there's multiple things that are happening during the workup. Okay? Kind of our the workup is kind of taking care of everything that's remaining from each of our steps, because up till this point we just kept putting in more into that round bottom flask. Well, now we need to get rid of the things that haven't reacted. So the first thing is we're going to get the formation of our alcohol. That's what we want out of this workup, okay? So we'll form our alcohol, and we'll have some MgBr plus kind of floating around in that aqueous solution. If we have any Grignard reagent that did not react, we'll get rid of that as well, okay? Because we've kept all of the water away from our Grignard reagent. Well, now we're going to kill our Grignard reagent, so we form the corresponding alkane of our Grignard reagent, more MgBr+. We're also killing the end of our magnesium that's left. And so we're forming magnesium sulfate, and you're going to see hydrogen gas being given off. So that's the bubbling that's occurring while this magnesium is reacting. And this magnesium sulfate is the solid that you then need to watch out for at the end of adding the sulfuric acid. So you want to make sure you don't have any solid left before you go to add it to your separatory funnel. If you do have white solid, you need to get it dissolved. So follow your lab manual, because it tells you how to add water to it to get that white solid completely dissolved. Wait until you've added all of the acid before you decide whether you have too much magnesium sulfate or you have any solid because you're going to go through different phases through the addition of the acid and through the workup. Okay, so wait till the end of the workup to decide if this is a problem or not. And then, like I said, if you have any magnesium left over that doesn't react, then we'll filter that through some glass wool. Now with glass wool, you've got to be careful. It's glass, okay? It's thin little pieces of glass. So wear gloves when you handle it so you don't get any glass in your hands. It's like handling fiberglass. You don't want to get any of that into your hands. The other thing is, make sure that this bubbling has ceased before you put everything back into your set funnel too. You don't want to be giving off gases when you're going to put something in a set funnel and you're going to be capping it, and then you'll lose the cap because you're building up pressure, okay? All right, so once we are ready to put everything into the set funnel, we're going to use two different terms here. We're going to extract and we're going to wash, okay? And so on our flow chart here, we're separating our layers, okay? Then we're adding ether for the extraction. So this is our extraction. And then here, we're looking at the wash. So I'm going to explain what that means. Whenever we talk about extracting an aqueous layer, extracting a layer during a workup, that means that that layer has something that we want in it and we want to take it out, okay? So we're extracting the aqueous layer with ether, and this time you're using red can ether, okay? So we've added water, we're not keeping things dry anymore, we're not going to worry about using that super dry ether that we use to form our Grignard reagent. We're going to add the ether to our aqueous layer, and it's going to extract, take out of the aqueous layer any remnants of our product that's still left in that aqueous layer, okay? So extract means we want to take out of that layer, in this case with an organic solvent. They sometimes can go the other direction as well, okay? You're going to have two ether layers then, okay? Because you've separated your two layers. You have aqueous layer, ether layer, and then that aqueous layer we are extracting with ether. We're going to combine those two ether layers, and then we're going to wash the ether layers with sodium bicarbonate. Okay, so we have sodium bicarbonate solution, it's 5% solution. The wash means we want to get something out of the layer we want to keep. So we're going to keep the ether layers. We want to wash something away from those ether layers. All right? So keep in mind what extract and wash means, because you're going to see these terms multiple times now whenever you do an aqueous workup. In extract or in wash, that means you're going to add whatever you're adding to a specific layer. So the aqueous layer, we're going to add ether to the set funnel. We're going to shake and vent the set funnel, and we're going to drain the aqueous layer. All those steps are implied in extract. That means do all of those steps, okay? Same with wash. We're washing the ether layers with sodium bicarbonate. So we're going to have our two ether layers, add the sodium bicarbonate to them, shake and vent, and then drain the aqueous layer or drain the lower layer. That is what's implied in wash, okay? Now with the sodium bicarbonate, it's reacting with residual sulfuric acid that is left in your ether layers. Be careful because it's going to bubble a little bit. So you don't want to start your shaking and venting until that bubbling has ceased, okay? And here you want your pH to be about neutral or so with the bicarb, okay? Or, pH 7 to 8, okay? We don't want it acidic, because if it's acidic, the next step, actually 2 steps in, we've got to do distillation. We're going to add heat, If it's still acidic, we're going to get a lot of alkene formed, and we don't want that to happen. Okay? So if you don't have a neutral pH here, do that wash again to make sure you get a neutral pH. And remember, when you're checking pH with a workup, you're always checking the aqueous layer, okay? Not the organic layer. All right. So now we've got our ether layers. They're all combined into one layer. We washed them with sodium bicarbonate. New step that we haven't done before is we're going to use what's called a drying reagent. So on our flow diagram, we've done our extraction, we've done our wash, we're right here. We're going to use our anhydrous magnesium sulfate, okay? So we're going to use our drying agent. What happens, and we use magnesium sulfate, but also commonly used is sodium sulfate, and both of them work the same. Now this time, we add magnesium sulfate that's anhydrous, okay? And this is by the balances. So unlike the magnesium sulfate that we were forming during the workup, which was completely hydrated, this is anhydrous. When you get magnesium sulfate that's anhydrous in contact with water, it wants to form the hydrated form. So it really easily picks up water from a solution. Okay? So this ether layer, even though we drain the aqueous layer off of it, it's still going to have residual water in it. We need to get rid of the residual water, and so we do that by reacting it with magnesium sulfate. And this, the anhydrous, is free floating. It looks a lot like cooking flour. Okay? So when you put it in into an organic solvent, so it always has to go in an organic solvent, not in the water. That won't do us any good. It looks like flour when it's going in, or when you're dispensing it out of the container, it looks like flour. When it's anhydrous, it's still free floating. When it's hydrated, you get clumps. So what you're going to do is you're going to add the magnesium sulfate to your ether layer, swirl it around, and what you should have is some clumps with a little bit of free-floating magnesium sulfate. So if you add it to the ether layer and get all clumps, we need to add a little bit more. If you add it to the ether layer, swirl it around, and you've got clumps and free-floating, you've got plenty, okay? Now, your lab manual gives you a gauge for how much mass to use of magnesium sulfate. You really never weigh out magnesium sulfate because how much you need depends on how much water is in your ether layer, how much is in your organic layer, okay? So you add magnesium sulfate till you get a little bit, you want clumps with a little bit less left that's free floating. And so when you swirl it around, it looks like a snow globe, okay, if it's floating around. So you want clumps with free floating. What you don't want is to take it to the extreme with the free floating and basically make like pancake batter. You add so much that it's a bunch of solid in that ether that won't even move around. Okay, so you want to be able to swirl it around in your flask. Once you've swirled it around really well, you've got your clumps with free floating, cover your Erlenmeyer flask with saran wrap and let it sit about 10-15 minutes. And then you're going to filter the solid with gravity filtration. So we don't want that solid. Your product is in the ether. It's an oil in the ether. Make sure you rinse. Now, rinse the solid with ether. And now we've dried our ether solution, so we don't want anything wet in there. But we can use the red can ether, okay? The red can ether is dry enough for this point. Okay, so rinse the solid well with ether. We want to get all the solution, all the ether solution off the solid because that's where your product is. And then we're going to, once you have all of your ether solution filtered away from the magnesium sulfate, you're going to use a simple distillation to remove the ether. You're going to do this with a hot water bath, so make sure it's a good hot water bath. While you're waiting your 10 to 15 minutes with your magnesium sulfate, get your simple distillation ready, okay? You have to get through this point this week. You have to finish the simple distillation. So there's a lot of steps involved. You have to get to the point that you finish the simple distillation, okay? You're going to store your product in a round bottom flask after the distillation with a slightly restopper. Now the last step is a fractional distillation. So we use our all-in-one simple distillation apparatus. Do a fractional distillation to purify our alcohol and collect just our alcohol. So you use your all-in-one simple distillation apparatus, similar to what you guys did last week with the styrene formation. You'll collect whatever boils before your alcohol should boil, and then collect your purified alcohol plus or minus about 20 degrees from its boiling point. And then whatever remains in your all-in-one simple distillation apparatus, or you make sure you don't go completely to dryness. The big thing here, make sure you know the boiling point of your alcohol, okay? And you need the atmospheric boiling point. It should be over 100, well over 100 degrees. If you find a boiling point for your alcohol that's below 100 degrees, it's not the atmospheric boiling point. So make sure you know this before you go to do this distillation. Otherwise, you'll keep what you think is alcohol, and there'll be impurities, and you'll throw your alcohol away. Okay? Now, this fractional distillation we can do next week in lab before we do experiment 11. So we need our product from experiment 8 for experiment 11. We can do this fractional distillation in lab next week before you start experiment 11. All right? Then your product, your experiment 8 product, you're going to want yield. You'll get boiling point information. You're going to want to collect the IR spectrum of the purified alcohol. And then in lab next week, we will make a GC sample, and you'll be getting GC data for your alcohol as well. Okay? And so next week, besides experiment 11, the dehydration experiment, I'll also be talking about GC gas chromatography. That's what's in experiment 10, is the gas chromatography.